am given to the phi of B actually, the image and output of it. Okay? So if Q is B composition phi, okay, Q is B composition phi, and you want to compute the fresh derivative of the Q, okay, at the point A, okay, at the point A or at the point B, okay, how can I compute it? So how can I compute the fresh derivative of it? So if I write in a matrix form, so I'm going to say the Jacobian of the Q, okay, evaluated at, say for example, okay, B is equal to Jacobian of
phi.
Okay, B evaluated at A and Jacobian of the phi evaluated at B actually.
Yes.
Did you see this? So that's B and that's phi of B actually. Okay? So you have this result. Okay? So we know this result. It's not a big deal. By the way, what would be the dimension of these two matrices? Can anyone guess? P is a map not from R2 to R3, so that's a map in R3 actually. So to R3. So it's a map from R2 to R3. So what would be the dimension of these two matrices?
So Jacobian of P जो होगा वो 3/1 का मैट्रिक्स बनेगा.
3/1.
Yes sir.
क्यों? So अगर it's a map from R2 to
अच्छा
R3.
ये 3/n ये u सर n dimension.
नहीं U 2 dimension में है ना. So U is
so r/2 होगा. r 3/2 sir.
3/2. So that's a matrix 3/2. And what would be the Jacobian of this matrix actually?
5b2 ये 2/2 का होगा सर.
Okay. So this is going to be 2/2. Is it 2/2? 5 is a map from R2 to R. So this is going to be 2/2. ठीक है? और Jacobian का dimension
3/2 sir.
So it's going to be 3/2. This is what an important point to remember. So the Jacobian of, if the phi is 2/2, okay, how does it going to look like? So it would be a 2/2 matrix. So let's give it a name actually. So the Jacobian of phi of B, okay, is going to be what? So this is going to look like something like this. So A, B, C, D, something like that. So it's a 2/2 matrix, something that is not known to me. What would be inside the Jacobian of, for example, P? What would be inside the Jacobian of P?
Jacobian of P is composition of B.
So P is like a map of P of U, something like that. So defined through some formula. Okay. So that if you take these vectors, write them in abstract form, and you take phi of this form actually. So what you can show, maybe it would be a good exercise to show that QU can be written as a linear combination of PU and PV in this manner. So A PU Q of B is A PU of A plus. Okay, so this A and this A are different. Okay, you have to be careful. And C PV of A. Okay, and QU of B, V of B is going to be what? B PU of A plus C P, what do you say? V of A.
Which A's are different sir?
ये B होगा और ये D होगा, and we're gonna have QU and QV. ठीक है? It should be the same case actually. So I'm doing what? I'm saying put the values of A, B, C, D here and put the value of matrix what do you call, that we just wrote actually here, and with the value of matrix here, and just multiply it, you're going to see, and write it back in a vectorial form actually. So the PU is a vector now. It's not just a, what do you call, a number, it's a vector actually. Okay, so what we are saying that you will see that you can write the QU as a linear combination of PU and PV, and QV as a linear combination of PU होना चाहिए, PU or PV. Yes, I'm writing correctly. ठीक है? So that's QUs and QVs can be written as the linear combination of PUs and PVs, where the constants involved in linear combination are the the vectors of the columns of basically what do you call the columns of this Jacobian matrix of the phi. Okay? And then you can compute the QU cross QV. Can I compute QU cross QV?
Yes.
I can compute it. It's not a big deal. So I can take this vector cross this vector actually. Okay? And I can apply the distributive properties and distribution of the cross product over addition and so on and so forth. So what would be the first term? A B PU cross PU.
0.
And you're gonna have A D PU cross PV, and C B PU cross PV, and C D PV cross PV. So PV cross PV and PU cross PU would be 0, so the only two terms will survive. So one is going to have coefficient, what do you say, AD, and other is going to have coefficient BC, but I can write a minus and I can write what do you call PU cross PV. So PV cross PU, I just switch the sign, change the, you get it.
So AD minus BC.
So what is this now? AD minus BT is
Jacobian
Jacobian.
determinant.
Okay. So this really completes the proof actually that it's the determinant of the Jacobian. Why? Because AD minus BC is really this determinant actually. Okay. So what is the moral of this story, this proposition actually? The moral of this proposition is that okay, you have a parameterization PUV that take you from R2 to R3, okay? And you have a reparametrization of it, but you are reparametrizing it through a diffeomorphism. That diffeomorphism is going to preserve the areas. Okay, not only preserve the areas, but the vectors are going to be multiples of each other. Okay, so in other words, these vectors are going to be linearly independent with this, linearly dependent actually. So these, like this vector depends on this vector actually, okay, with this coefficient. So they are linearly dependent, one thing. And I mean, if you take their magnitudes, okay, then you will see that diffeomorphism property coming out, that it respects the area. It kind of assist you to equate the areas actually. The area spanned by these two vectors is going to be equal to Jacobian, determinant of the Jacobian time than the area of this basically. Okay, so it's like there will be multiple of each other. Okay. Good. So that's a key property, an interesting property. And now let me define a few things. Define a surface, define some of things precisely. Alright, so let me write the first definition. So here's the definition. So I'm going to say if you have a smooth map, P, that is a map from a subset of R2, an open subset of R2 to R3, where U is open in R2, it's an open subset of R2, and I'm going to call such kind of a map a regular map. I'm going to say that its it's regular. So what do you think? What should be the definition of it?
डेरिवेटिव जब लेंगे उसमें जब आप जीरो पुट करेंगे तो वो जीरो नहीं आना चाहिए.
Partial derivatives actually. Okay, partial derivatives. Now, how can you make sure that the both of the partial derivatives are not zero with respect to u and with respect to b in a single statement? Can you give me a single statement which will ensure that none of them is zero? Yes. So their cross product should be non-zero. Okay. So it's going to be regular if pu and PV are linearly independent, okay, that is equivalent to say that PU cross PV, the partial derivative, these are partial derivatives of U, and PV is non-zero. Okay, PU cross PV is non-zero. So that will be the meaning of a regular map. And where PU cross PV is zero, you're going to call, in other words, those points where PU cross PV is zero. So you have to keep this in mind that this is going to be a function of U and V. So everything is going to be a function of U and V. So PU is a function of U and V itself. It's a partial derivative. PV is a function, so the cross product is a function of U and V. Okay. So that point. So if this is true for the entire domain, then you're going to call it it's a regular map actually. Okay. I'm going to give it a name soon. They will give it the name path, but I'm not going to call it a path because it's no more a path actually. It's not a curve. It's more than a curve actually. Okay. And what is the next thing? The next thing that I'm defining is this. So that's the first part of the definition. The second part of the definition is that if you take a regular map, So how did we define a curve? We defined a curve as an image of an interval actually. Okay. So it's an image actually. So in R3, if I have a path, okay, that takes me from this interval I into, say, in this R3, okay, then the P of I, the collection of all outputs of the interval I, if you put them together, if you make a graph of it, that's gonna be, a curve actually in R3. So what do you think? What should be the definition here for a surface, roughly, a parametric surface? So instead of interval, now you have a U, that is a region in 2 dimensions. You're going to say you have a region. Okay. So instead of I, you have a region. And instead of curve, now, so if you map this entire region under, what do you call, a suitable map, which is going to be a regular smooth map, okay, regular map, then you're going to get something like this in 3 dimensions actually. And you can treat this subset of R3 as the image set of the U. And I'm going to call this as the surface actually. Okay, I'm going to call this as the surface. So previously the curves were identified by path, regular paths. So here the surfaces will be identified by regular such kind of maps actually. Okay, parameterization. Okay, is it making sense? It's very analog. Very analog actually. Okay. Alright, so let me write a precise definition. So a parametric surface are simply surface actually. Okay. S is a subset of R3. It's a subset of R3, but it's a subset of R3 of what kind? To gather regular map together with a smooth, I shouldn't say smooth because if I'm calling it regular, it's smooth already. Together with a regular map P, that P is a map from U to R3, where obviously the U is subset of R2, okay, such that what should be the relationship between the P and the S? That if you compute the image set of the entire domain, you should get this set actually. You should get this set. So that's the definition of it. Are you getting the point? This map P, okay, we call it a parametrization actually. Okay, we're going to call it a parametrization. So it's a parametrization of a surface. Okay. As for the curve, for doing all calculations, the path was the pivotal thing. What is the parametrization of the curve actually? You look at it and then do the calculation based on it. So whenever you hear a surface now, you're going to always ask, what is the parametrization of that surface actually? Okay? And then the surface is basically the image of the parametrization map actually. Okay? Is it making sense? Good. So another map, so let me write this more formally. So a map Q, that is a map from V into R3 such that can be written as P composition phi. Okay, P composition phi, where phi is a map from V to U, and V is a subset of R2, obviously an open subset of R2. Okay. Then this Q is called the reparametrization of the parametrization map. Okay. And this Q, where phi from V to U is diffeomorphism. Okay. And what was the definition of diffeomorphism? That is that it is bijection. Okay. It's bijection and its Jacobian is non-zero actually. Okay. And the determinant of the Jacobian is non-zero. Okay. Then such kind of a map Q is called a Jacobian map actually. The reparametrization. So you take a diffeomorphism, you and you take a parametrization. So if you reparametrize the parametrization of a given surface through a diffeomorphism, we're going to call this Q as a reparametrization. And what would be the key thing about, the good thing about the reparametrizations? We already saw one of the interesting consequence of it, that this interesting QU cross QV vector, we're going to give a name to it, is always a multiple of QU cross PV. Okay. You can add a quick remark here. I mean, if you see, I can write it, but you can already see that if in addition you assume that your P is regular. So if you assume that your P is regular, in other words, PU cross PV is non-zero, okay, then Q will also be regular actually. Can you see why it should be regular? Because this guy is non-zero, and Jacobian being diffeomorphism is non-zero, so that's not zero actually. Okay, so in other words, if you take a regular parametrization and compose it with a diffeomorphism, okay, its regularity is preserved actually, it's not gone. Okay, the regularity of the reparametrization is going to be preserved. So this is an interesting thing that we should call it actually. Okay. So there we define then after the curve. So once we have the curve, then we say that okay, you should have the oriented curve actually, and then you can have the reverse curve and all that actually. So you can also have a similar kind of a thing. So you have a surface, an oriented surface, and reverse surface. By oriented surface, what do you mean? Roughly, for example, I can give you an analogy. So if I'm moving around this table, okay, in one direction actually, so clockwise and anti-clockwise, this curve is always going to be, for example, if I am moving, this way, then around this table actually, okay, around the boundary of what you call surface. So I'm going to say that this will always be on my left actually. Okay, so it's an oriented kind of a curve. Or if I'm moving, for example, counterclockwise, it would be always on my right actually. So it has an orientation. It's not like a Mobius strip actually, in which you don't have inside and outside actually. Have you thought of Mobius strip? It's an interesting piece. Can you think of something which doesn't have inside and outside? Inside and outside.
So you are giving an example of
that
this.
doesn't have an inside and outside. It would be a difficult thing to imagine. But what you can do is that take a strip and make a Mobius strip out of it and think about it. If you move inside out of it, a time will come when you will be outside. So the inside is outside. So for example, if I'm moving inside the room, I'll always be inside actually. I'm never gonna get outside. Okay? Or if I'm moving outside the room, I'll always be outside. So this will not happen that okay, I'm moving within room, within an object, and for a moment inside, and then miraculously I come outside of basically that object. So Mobius strip is such kind of a thing. We not get too much into it for now. So let's talk about some examples of it. Let's talk about some examples of it. So the first example is really a generic example. Okay. And suppose you have a scalar field f that is a map from u to r, where u is a subset of r2. Okay. And think about the graph of this map. So how can you have a graph of this map actually? Where f is smooth actually. Okay, it's a smooth map. So what you can say about the graph of it? How are you going to plot the graph? So you're going to have so it's a map in R. Okay, so it's like you are taking a region in R2. You are taking a region in R2 and assigning each point a height actually. Okay, so this is say UV. So UV, and this is like f of UV. F of UV. This value is like f of UV. But what would be the coordinates of this point actually?
So
This point.
UV and
So
f
it's going to
of
be UV,
and f of UV.
and the height of it is
F of UV.
Very good point. So if you take all these points, okay, and graph the heights of all points within this region, so you're going to get some kind of a surface as a result actually. Okay? Can you see this? So as f is the collection of the graph, and there's an interesting benefit of it actually. So f of UV such that UV are U actually. Okay? So that's a graph of the map F, you define it. So that's a surface. This surface, we call it a graph surface actually. Okay? It's a graph surface. Question, is it really a surface? So if it is a surface, you need parametrization. So can you think of a parametrization? So what should be the P that takes me from the point here to the point here actually. So what should be its definition? So the P of UV should be, so P is a map. Let's define a map from U to R3 by that I have a P that takes the value UV and gives me as an output the image of that, what do you call, output under the F actually, under the point. So you're going to have UV and okay. So P is a parameterizing map that takes every single point from the domain and associates them with the point in the surface. So that would be the parameterization of it. Now, this parameterization would be a parameterization really if it is smooth. So is it smooth? So smoothness is not trouble. So U and V are linear expressions, so they are smooth. But third component is also smooth because we have assumed the smoothness. Okay, so all three components of this vector are smooth, so this is a smooth vector field. There is nothing trouble with it. So what else you need? You need to also check the regularity. So how are you going to check regularity? So let's compute say PU. So what would be PU? The partial derivative of the U. It's going to be 1, 0 and FU. Okay. And what would be PV? So it's going to be 0, 1 and FV. Okay. So what would be PU cross PV? I'm not calculating, I'm just writing it directly. I'm writing it directly. So the PU cross PV is going to be, we're going to compute it, minus FU minus FV and 1. That would be the PU cross PV. You can compute it and you will see that this will be the PU cross PV.